I'm a partner with A.T. Kearney. And I'm very pleased to introduce our panelists today. To my left is John Tilko, Chief Innovation Officer of Aurora Flight Sciences. We also have Martin Rowe-Wilcox, Head of Business Development of Future Combat Air Systems of BAE Systems. We're also joined by Dr. Jae-Won Shin, Associate Administrator of NASA Aeronautics Research Mission Directorate. And last but certainly not least, Bill Irby, Senior Vice President and General Manager of Unmanned Systems at Textron.
Hello.
So welcome.
Thank you.
Most certainly this topic of UAVs is something that it's kind of transcended the walls of the folks that are involved in UAS and UAVs for the last at least decade. Most recently in the last 5 years, the proliferation of it has made it more of a, we were talking outside, in some cases, the domain of the consumer industry, not only of the aviation. So the rate at which it's grown and it's changed just in the last 5 years is quite mind-boggling, as all of you know. So we want to explore today how far, what are the limits, whether technological or otherwise, of the UAV technology and penetrating the wider aviation industry. We're going to touch on 4 themes. The first one is what lessons can we learn from the military applied to the civilian world. The second one is the role and limits of autonomous aviation. We're having an interesting conversation outside of where are those limits. The challenges of integrating these kind of systems into the commercial airspace. And finally, a little bit about future vision. Where can we get to? So with that, perhaps we can just start directly with that topic about learning from the military. And I guess this question can be for either Bill or Martin. What lessons can we learn from the military in the proliferation of systems in the civilian world?
Okay, I think that's an excellent question. Given the recent history, when I say recent, let's say the last decade or so of military operations, UAVs have been used alongside manned assets very successfully for about at least the last 10 years. For example, we've operated some of our systems literally at the busiest airfields in the world. In fact, rivaling many of those of major commercial airports. We've learned to do that very successfully by coordination with air traffic management authorities, air traffic control, setting various vectors and parameters on where these systems can fly, how they're controlled, how they're used. And that's been done very successfully. At the heart of every one of these systems today is a human. And command and control systems are operated by people on the ground that have continuous visibility into what these systems are doing, how these systems are behaving, the aircraft, and every aspect of the system. So at the heart of it, there's still a human in the loop. When we get into the topic of automation, how far can that go? With the systems that we have today, even in that airspace, there are some automated functions and automation of those systems going on today. Navigation plans can be set, they can be preloaded, waypoints can be put in, and courses of those aircraft can be changed in flight. All of that done within a certain set of parameters and guidelines on how the system operates. So that's one aspect. Another critical aspect to success of that is in the area of training. And we can expand on that more as we go in the panel. But there is success today in UAVs operating in manned airspace for certain applications.
Very good. So Martin, would you be able to tell us a little bit about any R&D that is in the pipeline for you on applying technologies that you traditionally have used for military purposes in the civilian world?
I think the interesting thing is looking at how you take an operational scenario and put that into a civilian space. As Bill said, there's always a human in control. The systems generally, when you look at them, we always concentrate on the flying part. There's a piece on the ground as well. So when you're looking at an overall system, the flying element, the ground element, the communications network, and how that operates as a complete system. So putting that in a commercial space, where do those pieces fit? And more importantly, how do you become to more freedom to fly those systems going forward? What you find is these systems have a tendency to generate an awful lot of information. The military learning from the early days has been lots and lots of data, videos, or whatever else that need analysing. To commercialise that, I think we need to find a way of accessing and interpreting that data in a different way to get the actual manning footprint down. Because what you end up in an unmanned system is a lot of people. It's just there's nobody in the aeroplane. So the big lesson is how you actually get to a commercial offering that actually takes you from that one step across. The other thing I would say is get the end user involved early on. So it's very much this partnering relationship between the customer community and the system developer, and get those a lot tighter. So engineers will engineer things for you, but the answer may not be what they want to engineer. There might be a different place to go. So collaborative space between an end user to pull the technologist, I think, is again something that we'll probably learn from the work we've been doing. And therefore it's quite important then to sit down with all the players, including the regulators, the Civil Aviation Authority, air traffic agencies, or whatever those players might be. Because ultimately you want to operate the system, and a piece of airspace is a lot more open maybe than the military have been used to using over a battle space. So all the work we've been doing around airspace integration with what we've used as a surrogate aeroplane so we could fly it in UK airspace has been with a very wide group of stakeholders right through the process of how does an operation work, how do you engineer that, how do you certify it, how do you work with air traffic, and how do you fly 200 miles through 5 different types of airspace, realistically fully controlled by air traffic, with actually every other airspace user not realising that you're actually a UAV. So that's the sort of the step of how you get from the bits we learn and know about in the military domain, and how do you now start moving that into a more open space.
Right. And I wanted us to talk more about the integration to the civilian airspace in just a minute. But before we go there, you talk about integrating more with end users. Can you talk a little bit about the applications that you are foreseeing this in the next 5 years in the civilian world? And then I'd like to move on to Dr. Shin about what kind of applications are you seeing also in the US through your research in NASA?
I think a lot of people are interested in how you can take a surveillance operation into the unmanned space. Now, I'm talking here of things are the greater than 20 kilogram aeroplanes, so things with significant endurance, significant reach, but actually putting it into that commercial space. It tends to be the initial interest is around things like infrastructure and environmental disaster relief and so on. What I would say is a system designed for military operations might be at the wrong price point for those operators. So that's where the innovation is going to come in, as to how you actually take the pieces you want, but then maybe take them to a slightly different space.
Okay, very well.
Can I add just to that real quick?
Yes, please.
You know, that's a great point. When we look at commercial aviation and civil missions, one area to think about is environmental protection. For example, this past year, we were one of a couple companies that demonstrated systems for wildfire protection under the U.S. Department of Interior. And what we found was we ran into some of the same airspace coordination needs, but those were solved very quickly and the missions were flown successfully. And these systems provided value in the data analysis and the reports and the information that was given back to firefighters. So you can project very quickly that the more that these systems are used in applications like that, the more learning is going to come and their acceptance will be gained.
So the acceptance element is or can be one of the barriers for the penetration or the expansion of the industry, especially when you talk about larger size equipment. Jae-won, what kind of technologies, what kind of equipment, what kind of applications are you working on in the U.S.?
Right. From NASA side, since we are working on civil commercial aviation end of it, not the defense side, we have been working on certainly how to integrate UAS into national airspace, because you cannot have two separate systems or segregation. So number of key technology barriers there. First of all, sense and avoid becomes a huge issue, and also communication. And both Bill and Martin talk about humans in the loop. So until we go to completely autonomous system, we have to have a human in the loop, and this roles between machine and human is very tricky. So that by itself is a rich research topic. And then we also have been developing live, virtual, constructive, distributed test environment. So it's a long.
Say that again.
Live, virtual, constructive,
Virtual.
Distributed test environment.
What does that mean?
What that means is you can insert manned and unmanned, either real or virtually, and also the test sites or the control centers can be distributed geographically and tied together. So you don't have to be in all one geographical location. So it's been several years for NASA to build that, working with FAA, Tech Center, and several of our industry partners. So you mentioned about the experience and operational sort of experience. I think that's the really key, that when you introduce this new system, it is understandable that people feel a little bit of anxiety and worry about how it's going to work out. So I think the best way is really going through some actual practices and showing the actual application, not only showing the benefit, but actually operators getting more experience. So as an example, a very quick example, Bill mentioned about wildfire. So we have a Predator UAS at our Armstrong Flight Research Center in Mojave Desert area. So we actually deployed the Predator during the wildfire in the California area. Ran into a lot of issues, as Bill mentioned, not just air traffic control issues, but communication and all that. So we learned from that, and we're applying that back to our research. So even research stage, I think you have to continue practice these things.
Very well. I think that brings me to the issue of safety. So if you had problems with communication and so forth, public perception can be swayed pretty in a quite big way if there was to be an accident, especially of a big platform. And I want to bring in John here. What technologies or what are we capable of today, and what are we going to be capable of in, say, 5 to 10 years to keep these things safe and to keep society safe? And I'm not talking about the privacy issues, but just more specifically about safety.
Okay, I guess I would start with collision avoidance. So we will see systems that really improve the fidelity and capability of sense and avoid and other technologies to avoid collisions in the airspace. I think that's one of the fundamental ones. We're also working on programs that are designed to extend the relationship between humans and autonomy, and I think all three of the other speakers have talked about this. This is really at the core of the cutting-edge autonomy research that's being conducted now, to look at what is that sort of cognitive space in the cockpit between a human and an autonomous system, and looking at ways that the autonomy can aid the human to do a better job in the cockpit, because we've seen several of the recent aircraft accidents that are really dealing with humans' inability to perceive the state that the aircraft is in. Even with a multi-person cockpit, it sometimes can actually get even more confusing to determine that. So looking at states of autonomy, looking at systems that can assist pilots, looking at this very complex area of humans and autonomy and how they interact, I think is at the key of this forward direction in research.
Very well. So I think that we need to address the integration to the airspace. I think we've mentioned it several times. How will it be done? Let's talk a little bit about an operating model. How, first of all, and let's leave regulation aside, because we're going to have another panel specifically about regulation tomorrow. But how will we integrate all this into the commercial airspace? And perhaps we can start over there with you, Bill. And I'm not talking only about the technology, but it is about what organizations. Will the FAA continue to regulate this? Will we have to create new authorities? How will all this happen?
Right, it's a great question and a very complex one. We were having a little bit of discussion prior to the panel on the FAA and what exactly is their role and how does that apply to systems currently 55 pounds or below, and then what is the role when it comes to the very large systems flying at very high altitude. And there's been some work done by NASA looking at various aspects of that control. So the interesting question becomes, as the rule for the 55-pound and below systems are established, which are currently outside of controlled airspace in general, how do those rules and how do the models get integrated into successful regulations, policies, procedures that can then be integrated with the current national airspace that's generally, for higher altitude flights? Mm-hmm. It's a big question. There's certainly a lot of detail to work out. I think that, NASA, with their role in research, has a lot of things going on to help define that. But who is going to be the ultimate authority may well change over time, but currently it does reside with the FAA in the United States, and that's the rightful place for it, but things could change over time.
Martin, do you care to elaborate or give us your point of view?
I'd just probably add a few bits to what Bill was saying there. Very similar frame. We completed last September a sort of 7-year program in the UK called the Australia program, and that was looking at the regulations and the technologies required for opening the UK airspace to use of unmanned systems. And very quickly we got it down to some very simple phrases. First one is safe to fly and flown safely. That recognises the fact there's a technology part in there and there's a human part in there.
Right.
So how you actually regulate the use of the system and the training requirements and so on, but as well as that, it's not just a technology problem. The other little strap lines were around recognising that to introduce a new type of user into airspace, let's face it, the UK is a fairly crowded little island, so we have lots of little bits of airspace. Then effectively the use of the airspace to the UAV user has to be equivalent to that for all the others. So equivalence on one hand and transparency on the other. In other words, every other user need not know you are an unmanned vehicle. You are just an aircraft to them. Mm. So if you're flying in the airspace, you're just an aircraft. And therefore, when you actually, if air traffic control need to talk to you because you're in a piece of regulated airspace, they need to talk to somebody who's in command of that vehicle as if they were physically sat in it, even though they might be thousands of miles away. So it's now taking the operating model that the military become very comfortable with, as far as a remote location for the man in command of the vehicle, and now saying I have to put that into a completely civil commercial space with air transport, civil airliners, general aviation aeroplanes, parachutists, gliders, whatever else might be in that airspace. That's quite a complex model, but if you keep the simple lines, transparency and equivalence, you then get yourself to a point, you have to work your way through that. I'll give you one very simple worked example without hogging the stage. Yeah. 11 years ago, we had a little research aeroplane called Hertie. We built it out of a motor glider. We converted a motor glider into a technology research vehicle, and we needed to go flying, and we wanted to go flying in Scotland. And it took us 5 months to build the aeroplane. It took us 9 months after building the aeroplane to get the civil regulator comfortable with us flying that aeroplane for 9 minutes. That was because there was no regulatory framework. There was no rule set. We actually had to sit down, and on the safety side, we actually had to step through every part of the mission we wanted to work through and work out what exactly would happen if there was a failure at any one of those points. You can then build that into the way you design the system, into the way you build your mission plan, and all of a sudden you find out, yeah, it is feasible. So everyone that says no way at the beginning, slowly but surely could understand. And I think that's a very tiny example. Take that to national, international standards, and all of a sudden there is now a groundswell understanding of what those steps are needed. We're not there yet, you know, the different national players are playing there, but we're not, you know, we're getting in the right direction.
So we've been talking about still, so unmanned vehicles, but commanded by humans on the ground. Jae-Woon, in the research that you guys are doing over there, when we start integrating completely autonomous equipment on the air, what different way to manage the airspace are we going to have to confront?
Yeah, so as Bill alluded, it's very complicated issue. So 5 years ago when we started UAS integration into a national airspace project, we all were thinking about large, very sophisticated and well-equipped UAS getting into well-controlled airspace. So that presents a set of issues, but over the time, our focus really has been shifting, or the whole communities, at least in the US, whole communities' attention has been shifting to this so-called small UAS, 55 pounds or less, operating at 5,000 or below airspace. As Bill mentioned, it's not controlled airspace at the moment. It's not the uncontrolled airspace, but it's kind of wild, wild west out there. So how do you...
That's the US.
In the US, yeah. So how do you do this? We thought integrating, again, well-equipped, sophisticated UAS in the control airspace was hard enough. But this low-altitude, small UAS operation presents a whole different set of challenges. So I think one point I want to just interject here is because of the pressure of the market demands and the players in this low-altitude operation, we could face yet another very stovepipe sort of evolutionary, as needed, need-based approach. And 20 years later, we'll have to start overhaul the whole thing, just like the current ATM system has gone through. So from NASA's perspective, this is a really golden opportunity to actually approach systematically, well-concerted, well-thought-out approach for small UAS operation at low altitude, so that the system, whatever the concept and system that we're developing, can be scaled to the massive volume of UAS coming into system. We think we have a chance to do that. We're much smarter than 50 years ago, so we can do that. But the challenge is the market demand is so strong. If we are not careful, we're going to fall back to just address individual requests for certification and individual system. And then before we know it, there will be 100 different systems.
So who's taking the lead, right? So the market is ahead of regulation right now, right? Actually was reading an article in the Economist about a year ago that our projections for growth in 2010 for the next 10 years of UAVs for the entire base of UAVs that were going to be in the air was going to be about 15,000 in the US. And now we're selling those per month. So who's taking the lead to regulate this or to organize it and to build the structures and the governance and all of that needed to manage?
Yeah, so very quickly, and other panelists probably have good answers as well, but in the civil side, I work almost now weekly with my counterparts at FAA. So Associate Administrator for Safety at FAA is really the responsible person and organization for this. They are doing everything they can. I can see that every day. But because the safety is really paramount and that's their charter, and the whole cultural issue comes in as well for FAA. So it's very difficult and challenging, but at the moment in the US, I think community also, the small US community, agreeing that FAA needs to lead. And NASA can play, again, as a technology enabler or provider and working with industry. So if we can do that public-private sort of partnership right, I think we can address this problem and solve the problem. But at the moment, it's a little bit nebulous, like you're saying. Who should be really leading and proactive? Because a lot of people think, somewhat unfairly, I can say, that FAA is not proactive and moving fast enough. But again, from where I can see in daily interaction with FAA, I think they're really trying to do their best.
Very good, thank you.
Can I just add to that? I think NASA's initiative, the UAS Traffic Management, UTM, which evolved out of the Ames Research Center, and Jaywan has been very supportive of. We see that as a really important initiative because effectively what you're doing is creating a new airspace. So a definition of an airspace that could be applied to areas like agricultural lands at a low altitude, defining a new airspace which then the FAA would ultimately regulate, but with technologies that NASA and the non-traditional aerospace community develops. So Aurora is very supportive of that initiative.
So John, I guess continuing with you, let's start talking a little bit about what's the road ahead. What is to come? You've been in the news recently with an award for research of the X-plane. Can you tell us a little bit about where will autonomy take us? Where is our current thinking?
Sure. Well, I said earlier about this important confluence of humans and autonomy, and it's really a trade space. I think we're increasingly thinking that manned and unmanned are two categories that aren't necessarily the right categories to think about this problem, that you're really seeing hybrid applications, you're seeing optionally piloted vehicles that can function either manned or unmanned. For us, optionally piloted vehicles with safety pilots on board has opened up a new dimension of R&D space because we can now fly under FAA rules in the civil airspace from any airfield in a fully autonomous operation with a human safety pilot on board. So it's really caused us to think more about the future in terms of what does the pilot actually do. So perception, both outside of the cockpit and inside, are critically important. And we have today some of the largest U.S. government programs in autonomy sponsored by DARPA and by the Office of Naval Research, which are really looking at the way that you could actually fly an unmanned aircraft using very advanced perception. So in the case of the ONR ACUS program, we're actually flying a helicopter into an unimproved landing zone that it's never seen before, and doing that at a very high speed using scanning LiDAR systems to test the safety of the landing zone. I call it the Apollo 11 problem without Neil Armstrong on board, because you're basically coming into a very complex territory. The purpose is for the U.S. Marine Corps to deliver supplies and eventually perhaps even to be able to do casualty evacuation with an unmanned aircraft. So That's an example. That could also be applied to civilian applications along the same lines of casualty evacuation and moving critical care patients to hospitals. So we're pretty excited about the direction that's going. And the same thing with perception inside the cockpit. Our effort is really reverse engineering the instrument panel of the flight deck, which is the common interface that all pilots use. Using vision-based systems, you can actually calculate the state vector of the aircraft and all the other critical parameters that the pilot is reading, and then use that information to assist the pilot.
Okay, very good. I think just because of time, I'm going to open up the floor for questions. I understand there are microphones throughout the floor. Yes, sir. Do we have microphones? It's on its way.
Thank you very much. My name is Commodore Samadar. I'm CEO of Shinmeva India. This discussion so far is about the vehicle itself, and we have seen that the advances in technologies on automatic takeoff and landing, automatic flight control systems, certainly detect and avoid, if not sense and avoid. These technologies have advanced to a large extent. But finally, when the UAV has to find applications in the overall aviation space, the two other factors which will come into play is firstly the payload it carries in terms of its utilization to society or in its ability to create new customers for an aviation requirement, and secondly would be the propulsion system. Briefly on payloads, we have the standard set of payloads, but in the future we'll be looking at full edge penetration radars or ground penetration radars, or being able to identify hotspots or corollas in power grids, being able to detect tigers in a reserve or whatever. So that's part on the payload side. So that would be my first question, that whilst we have addressed the vehicle part of the UAV space, what happens to the payload and how that is going to move forward in the years to come? That would be to John. As far as propulsion is concerned, being able to be at 55 pounds and below the 4,000 feet ceiling requires a completely different set of propulsion technologies so that you are able to have sustained operations. So my next question to Dr. Shin would be on how do you think propulsion technologies in UAVs would impact the overall aviation space? Because once you combine both of them, you are now opening up a completely new market for aviation, for UAV products, particularly where you are challenged with these issues about traffic on roads or tigers in forests or power grids or whatever. Thank you.
Thank you. John, do we want to start with your question? And was the
Sure.
question about amount of payload?
The types of payload. I mean, you already have electro-optics and so on and so forth, but whether you would carry hyperspectral scanners in the future, whether you would carry foliage penetration radars, you have ground penetration radars, corolla sensors. These are the sort of things which will completely transform the aviation space. A UAV is only as good as the payload it carries. So unless we can think of the payloads together with the vehicle, its applicability in the aviation segment will be only incremental. We're seeing a lot of improvements in it, but technologies in payloads and propulsion systems will also match.
Okay, so you mentioned several of the technologies the military is pursuing for more improved ISR type applications. I would look at the commercial sector, and what we're seeing today is significant innovation occurring in non-traditional aerospace companies primarily in Silicon Valley or in Cambridge, where we're pursuing things like telecommunications, so providing worldwide internet using UAVs for that purpose. So there's a significant amount of effort there, and I think that effort is important because it's operating at Moore's law, which is 18-month time cycle. So the rapidity of innovation that's happening on the payload side really needs to be matched on the aircraft side, and my company is trying to do that. So how do you bring Moore's law to bear on aircraft the way it does on electronics?
Can I just do a quick build on that one, because it's interesting that this whole concept of the payload. the payload is the reason there's an aeroplane up there. So at the end of the day, it's a bit odd for an aircraft guy to say this, but actually the most important thing is the payload, where you want that payload to be, how long for, what do you want to get from it, either real time or recorded. And it's unusual to have a conversation that starts with a payload. It usually starts with, can you carry this on your aeroplane, not the other way around. Recently, we've had the first conversation with a brand new end user I've never worked with before, who came to us and said, this is my payload. I need it to be carried to this place, this accurately, for this length of time. How do I do that? And to some extent, that's an element of the market environment now maturing to the point where those conversations come that way around. So it's not how much can you carry on an aeroplane, it's could you build me an aeroplane that could carry this for me?
Right.
I'd like to suggest, though, there are design principles. Both of you brought up great points about the aspects of the aircraft and the payloads. Some design principles on the aircraft, though, could very much help facilitate the payloads that are able to be brought on and solve different types of missions.
Right.
If conceptually, if you view your aircraft as a truck that can carry multiple payload types, and what does that mean? Well, you know the capacity of the aircraft from a weight perspective. You know the capacity of the aircraft from a power perspective. Now, have I put in it the physical and interconnect and electrical interfaces that are standardized enough to be able to adapt a new payload relatively quickly? Then I think we're getting the best of both worlds with an adaptable aircraft and commercial-based payloads that can be inserted at relatively low cost and rapidly in terms of time.
And then we get into how fast can development of new capabilities in the existing systems can come to market. I don't know can you expand a little bit on the new requirements that are emerging because the technology is getting there? And this would be for any of you four gentlemen.
Well, I'll go first if you want. One of the things that we do is do rapid prototyping that's enabled now by additive manufacturing. So in the case of this DARPA program that we were just selected for, an X-plane, vertical takeoff and landing X-plane based on hybrid electric propulsion, I think the winning factor, the reason we were selected, is we went through 4 design cycles in the phase 1 program. And that enabled increasingly better technology to be implemented on the structure and the aerodynamics. So this was basically design, CFD, make a 3D additive build of the prototype, put it in a wind tunnel, come back and iterate the design. We did that 4 times, and that resulted in a much more advanced prototype vehicle at the end of phase 1. Most of our competition was able to just do 1 design. So that's part of, I think, what the kind of change in the paradigm to go to achieve rapid prototyping. If this industry is going to achieve that goal of getting more onto Moore's law of 18-month design cycles, that's what's needed.
Yeah, I'd echo the rapid prototyping as well. I mean, we've got experience where, again, and the business has to put its own money down and say, I'm going to trust my R&D guys, I'm going to give them 12 months, 18 months, whatever, to prove an idea and then take that idea forward to the customer before he funds the full program. And effectively, that's how we launched the Trinus program in the UK, was by us doing 3 or 4 cycles before it, very similar to the way in which was described before.
Very good. Now we have time for one more question.
Just 1 second. There was a question on propulsion systems for UAVs that I had asked Dr. Shin to respond to.
I'd like to give the opportunity to one more question, and we can take the propulsion offline, if that's all right.
No, my second question was on propulsion systems to Dr. Shin. Maybe you'd like to respond.
I guess we'll take the propulsion question.
Yeah, as John was saying, we are looking at a UAS propulsion system more from the electric systems. So perhaps the small UAS side, there is just a limitation that you have no other choice. Even the larger UAS, I think the key point is how to actually converge all these somewhat seemingly disparate technologies. I think that's the point you are getting to. But how to capitalize on all these advances from certainly autonomous systems, electrical systems, and even vertical lift capability, as John mentioned. And I too agree that if we do this smartly, and I think we're kind of looking at the new dawn of new era of aviation. So, you know, we discussed about rapid prototyping and rapid introduction of technologies. NASA is really about long-term revolutionary technology and capability development. But in this area, if we really look at converging these different technologies, we may not need to wait 20 years to bring some completely new capabilities. So I know there are some outfits in the US working on air taxi kind of concept. So that's just one example. But there could be many other applications that we could only dream about today, but in 10-year time it could become reality.
Very well. Well, with that, I want to thank our panelists for your time today. There's an application, there's an app for the conference. If you have it in your phone, you can open the program section and go to this session, and there's a poll that you can fill and asks questions about this topic. And I believe the results are going to be made public either tomorrow or through another means to all the participants. So with that, please help me in thanking our panelists.